Hello. Let's continue talking about resonate. No. So we have been talking about in our applied nonlinear dynamics about limit cycles. Now I'm going to delve into it an application further. So one application of where we need to study or essentially generate limit cycles is in resonators and oscillators. We're particularly talking about, for example, in modern applications, we have MEMS devices, and many MEMS devices are used to generate these limit cycles for various applications. For example, one of many applications is that if you think about the Coriolis gyroscope, the way it works is from basic applied mechanics. We know that we have this Coriolis force, which is 2 omega cross V, and the V in gyroscopes is the V in the sense, in the drive direction, which generates a response in the sense direction. So we do need to have sustained oscillations just so that then we can use this Coriolis gyroscope to measure angular rate. So we have two things. Let's separate resonators from oscillators. Let's call our micromechanical component a resonator, meaning that we have a sinusoidal, for example, a steady state response with a peak near its resonance. But then this is an undamped system, but in reality we have damping. So this response is not a stable, sustained response. It decays by time. If you have an oscillator, it means that we also have proper circuitry around our resonator to sustain the oscillation. In other words, we create this system such that once we have the resonator, we can somehow sustain the resonance in that resonator. And this, as I just explained, it used in many applications. For example, in gyroscopes. For example, in timing application, frequency generation. Our fundamental goal is to turn a resonator into an oscillator, and it relates to applied nonlinear dynamics and nonlinear control. So I'm just trying to take a different approach. Once we have enough material to talk about a widely used application, we're going to delve into that application. So in this case, we're talking about resonators and oscillators. So we know that we can generate a resonance using, for example, a micromechanical resonator, or we can use a simple RLC circuit. An RLC circuit will generate a steady state sinusoidal response, but it decays the response with damping. In this case, the damping is our resistor. So if we were to rewrite this, we can simply apply, for example, Kirchhoff's voltage law in this loop and write down Vs minus Vct, the capacitor, minus Vl, the inductor, minus Vr equal to 0. The sum of the algebraic sum of all voltage drops is equal to 0 in a closed loop. That's essentially a statement of the Kirchhoff's voltage law. Once we have that, we can also describe the system in a state space form, meaning that one displacement variable and one velocity variable. So we have our two state variables here are the voltage across the resistor, and then we have the current going through the inductor. Now, if we define this V as here as our output voltage, we can describe our transfer function. So as a side point, pay attention that we know that a single circuit may have many transfer functions, more than one transfer functions, depending on the choice of input and output. That's a side point here. All right, so you could say that, all right, first off, we know that because R, the resistance is not zero, that ultimately the output goes to zero. But what if we manage to set R equal to zero? We can, for example, hypothetically, we can have infinite admittance, and then resistance for that goes to zero. We know that practically it's not possible, but this is one way to get rid of damping. So say we could have an undamped system. Then we can have a sustained oscillation. All right. The other way is like, all right, let me also explain this. But we have to pay attention that if you remember, if you look at the equation of motion for this system or for a mass damper, a spring damper mechanical system, you know that even if you don't have damping, what happens is that you have a system whose response is periodic, but it's not a limit cycle. All right. So again, this part is the part that relates to what we learned in nonlinear dynamics, that even if we don't have damping, the response is periodic, but it's not a limit cycle. In other words, if you change initial condition, we get a different periodic response. All right, so we're looking for this limit cycle because we want to have this sustained oscillation. Gyroscope, our gyroscope wants to have this V in the derived direction, which is stable, just so that we can then characterize the output with respect to our omega. One application. So, and this is a reminder to relate again the material to our nonlinear dynamics. The limit cycle was an attractive set. Now, what we're going to do for this application is that we're going to say, all right, what if I have a feedback loop? So we're going to also use the basic principles we learned in linear control theory or feedback control systems. That if we have a feedback, then we can somehow have R, but manage the R using our feedback. Now, the point is, if I have a feedback, if I, for example, use a unit amplifier and have this essentially being fed back, well, then what happens is this term cancels out this term completely. But that's not our desire, because if it cancels out damping completely, then again we are going to end up with the same situation we just talked about. We want to have a balance, therefore. We want to have a balance that says, all right, if our current becomes large, we can bring it down. If it becomes very small, we can push it up. Makes sense? So we look for that balance, because limit cycle is that stable isolated periodic solution that indicates that balance, that balancing point. So we're going to define, therefore, a feedback, but we're going to have this feedback, we define it in this form. tan inverse V0 over V2. And these are the constant parameters that we set depending on the parameters of the system. If we do that with this condition, A V1 over V2 larger than 1, what happens is that the linear approximation of this term is going to be AILR over V2, right? So if we have this condition, this term, or this term essentially, would be larger than this term, right? And this is what we're looking for. We want this to be larger than this one, and then for sufficiently large IL, we want to have this term becoming large. Again, back to that point that we want to have this system, we want to manage the energy in this system so that when we have excess energy, it could be spent using this term RIL. But if we are low, we want to have this positive damping essentially so that we can pump energy into the system. So we end up having this limit cycle. So this is the basis of what we talked about. So what I'm going to do is I'm going to try to have us upload the simulation to my GitHub page, but I'll further go through this later. Next time I'll probably I'll think about it, but for the time being, what you need to learn is, all right, so we had this limit cycle. To summarize what we did, so we talked about this RLC secret. This is super important in microelectromechanical system because we can then replace this with a micromechanical resonator which has a feedback loop for sustained oscillation. So if you look at this, the second term, the VS now is replaced with this feedback. This feedback has a limiter essentially, and what happens is that it cannot become extremely large, so it starts growing with this IL, right? But at some point it saturates, all right? And at that point when it saturates, then this term is still becoming large. So our damping becomes large, brings the system's energy down, and then again we are in the same situation. If IL is small, then this term is larger, so we pump energy into the system. So there is this oscillation between energy expend and energy pumped in the system. Thanks for paying attention.